So guys, in the previous class, we have started the concept of number system, right? So here we discussed various types of number systems. One is like binary number system, decimal number system, octal number system, hexadecimal number system. Like this, we have seen various kind of number systems, right? So if a number having a base with 10, I can call it as decimal number system. Similarly, if a number with base 16, I can call it as hexadecimal number system, right? And what are the basic characteristics of a particular number system? If I am trying to say that a number system having base x, the digits which are present inside here should be compulsory less than x. So I can call it as a maximum of x minus 1, right? So if I am going to have a number with radix r, what is the maximum possible number I can able to generate? R power n minus 1. What is r here? Base. N means number of digits minus 1, right? So for example, if I am going to have 4 digits and which is of kind of a binary number system, what is the maximum number possible? 2 power 4 minus 1, that is 4 ones. So 2 power 4 minus 1 is equivalent to 15, right? 15 means 4 ones. This is what we have seen, right? And also we have seen how to convert one number system to another number system. Like for example, if I would like to convert a decimal number system into any other number system, what we are going to do? We are going to simply divide. We are going to simply successfully divide the number with the destination radix. Similarly, if you would like to convert a particular radix number r into a decimal number system, we are going to simply multiply with r powers. This is what we have seen in the previous class. Okay. Now in today's class, we will see further. Basically, if you observe any kind of numbers, those numbers can be positive numbers, and the other kind of numbers can be any kind of negative numbers, right? So in another classification, this again further divided, like we can able to take a positive number can be of fraction once again, right? So if I am going to take 5.76, it is a fractional number. 5 is an integer and 0.76 is a fractional number, right? And I can call this number as floating point number also, right? Because here the point I am going to move from towards right side or towards left side. If I am going to place this point towards completely right side, this is normal integer value, right? If I am going to put this point value towards completely left side, I can call it as a fractional value. If I am going to combine these two, I can call it a floating point number. For this, I can able to append negative numbers also, right? It can be classified in many ways depending upon the number we are trying to represent. Okay, basically if you observe, it can be a positive number or it can be a negative number, right? Positive number, how we are going to write? If we are going to take the number like 5, are we going to place any sign here? No. As we are not going to place any sign, I can technically call it as unsigned number. One kind of classification is unsigned number, another kind of classification is signed numbers, because we are going to place here compulsory sign representation, right? If I am going to represent the negative 5, I am going to prefix with sign. If you want, you can able to represent plus 5 also, there is no problem. This one I can call it as signed representation. Okay, basically we are not going to place any positive sign symbol prefix with any number if it is a kind of unsigned number. Okay, in the system, how this negative number is going to be stored, that is the question, right? So while studying any kind of C language or any kind of Java language, you have studied some point like all the numbers in the C language or in Java language is going to store in the form of complementary system, right? All positive numbers are going to store directly, whereas coming to complement numbers like negative numbers, they are going to store in the form of complement of the actual system, complements of the actual system, right? So let me come to this point later. What do you mean by complement of a number system? Okay, fine. So before that, if you would like to represent the number 5, number minus 5 in the system, one of the representation is how we are going to represent the number 5. Can I call the number 5 as 101? Yes or no? 101. I am going to take one more bit, which is meant for sign representation. Sign representation, where I am going to consider 0 as positive value, 1 as negative value. 1 as negative value. Now try to observe what is the value of this one? 5. Prefix most, this one I can call it as most significant bit term. This one I can call it as least significant bit. Okay. If most significant bit is 0, I can mark it as plus. If most significant bit is 1, I can mark it as minus. And I am going to calculate the remaining value 5. This is what I can call it as negative number representation. Right? But the thing here is, if you would like to represent any kind of a negative number, there is no problem. It is easy for us to represent. But what about the system representation? Right? For example, I am trying to give two numbers 5 and 6. 5 and 6. And as I am trying to give 5 and 6, system will convert it into 101 and it will be converted into 110. It is going to calculate 1 1 1 0 1 1, that is 11. This is okay for you. Okay, fine. Basically, if it is binary system, they are going to prefix with 0b 101, 0b 110, so that system will understood that it is a kind of binary number system. So that it is going to get the result as 11 base 10 in decimal format, decimal number system. Okay, if now I am trying to give a number 0b 0101, 0b 1101. In my point, this is minus 5, and in my point, this is plus 5. What about system? How can we explain to the system that this is plus 5 and this is minus 5? We have to design the system in such a way that it has to identify always the most significant bit. If most significant bit is 0, I can consider as a positive value. Otherwise, I can consider as a negative value. Like this, I need to write the program for each and every kind of number in programming, right? But the thing is, this is a difficult task. And one more thing is, when you are going to represent any kind of representation in the form of like this, like minus 5 or plus 5, whatever the number representation, you are trying to perform some kind of operations, something like addition operation. If you are thinking that I am trying to perform addition operation, 5 over 5, what the system will do? System will generate the number 10 perfectly. There is no problem. If for the same system design, for example, this design is look like this. See, don't think about this is the exact structure. If you are going to give 5 and 5, it is going to give the result as 10. We have designed this circuit in such a way that it is going to work for the inputs of two numbers, both are of type positive numbers. There is no problem. But if I am going to give the number like 5 and minus 5, what the system will do? This circuit is meant for the performance of addition of two numbers, not for the performance of addition of one positive number and one negative number, right? So at the time, what you have to do? You have to design one more circuit like this. See, this is not the exact one. I'm just saying that you need to compulsory modify the circuit. Then only it can able to allow for performance of addition of one positive number and one negative number. So to overcome this drawback, what the earlier authors did is, why can't we take a single circuit? So that the same circuit will be used for both addition as well as subtraction, so that logic will be reduced, so that circuit design will be reduced. If circuit design will be reduced, our chip design will also be reduced. Am I right? Yes. I mean, if you observe here, instead of giving the 5 minus 5 as input to the system, Can I write like 5 plus minus 5? Can I write 5 plus minus 5? So that now the same input will be given to the same circuit. If I am going to get 5 plus 5, I can also give it to the same circuit. If I am going to have minus 5 plus 5, I can also give it to the same circuit. If you are going to get like minus 5 plus of minus 5, the same circuit will work for any kind of input, so that the same circuit will yield the same result. Okay, so this is the reason what the authors will come up with a new solution. That new solution we can call it as complementary of a system. Complement of a system. Okay, so here you have to understand one technical point. So sine numbers we are going to represent in the form of one way of representation that we have seen right now. This one I can call it as sine magnitude representation. Sine magnitude representation, where one bit will be completely allocated for sine bit, one is meant for negative, 0 is meant for positive. And in another way, I can represent the sine in numbers is one is b minus 1's complement format, and another one is b's complement format. Base complement format, right? So we have seen the drawback of existing system like signed magnitude representation, where we need compulsory different kind of circuits in order to perform various kind of operations. Instead of that, if you are going to learn the complementary of a number system, you can able to get only one circuit in order to perform various kind of operations, right? So first, what do you mean by complementary of a system? Right, observe. If I am going to have a number like x, what is the complement of x? I can represent like x complement, x bar, which you had in probability and statistics, right? So if I am going to have a probability of x is to 0.2, what is the other value of the probability? 0.8. Meaning that if I know the value of 0.1 value, I can able to get the value of another value. Meaning that if I know the complement of one variable, I can able to get the actual value of one variable. If I know the actual value of one variable, I can get its complement. Am I right? Yes. See, here similarly, if I am going to have a number like base 10, a number like base 10, whose actual number is 84. Actual number is 84, right? If you would like to find out the complement, if you would like to find out the complement, so how can we get the complement of a particular number like 0.2? 1 minus 0.2. What is this 1? Maximum possibility value, maximum probable value. Similarly, what is the maximum probability value of a number if it is in decimal digit number? If it is 10 tens base, we have come across that terminology already, right? If its base is 10, the maximum possible number is 10 power n minus 1, 10 power n minus 1, which is equivalent to 99. Right? If it is two digit number, right? So that is what, right? 10, if it is two digit space, I can able to get a maximum digit of 99. If it is three digit base 10, you will get 999. If it is something like base 6, maximum possible value is 555. 555. So what they are trying to do here in probability and statistics, they are trying to subtract it from the maximum value in order to get its other value, right? Similarly, if I want to get the complement of a particular number, what you have to do? You have to subtract it from the maximum possible value. What is the maximum possible value? 99. 99. From this 99, you have to subtract 84. 84. You will get 5 and 1. 15 base 10 is the one complement of 84. Is the one complement of 84. Right? Meaning that I can write 84 in terms of another form as 15 base 10. Right? If I would like to get the complement 84, actually what you can do? You can simply subtract again 99 from 15, you will get again back. That is what, right? If you know 0.8, if you subtract 1 minus 0.8, again you are going to get 0.2. 0.2, right? So this is the way you can able to find out its complement. Its complement, right? So here I have used two terminologies. One is b minus 1's complement, another one is b's complement, meaning that you can able to represent any number in the system in two formats. One is b minus 1's complement format, another one is b's complement format, right? So if you are going to perform it in the form of b minus 1's complement, you have to subtract it with the b power n minus 1 minus x. Is it correct? What is b here? Some radix b. I am trying to think that it is some radix b. N means number of digits, minus 1 means b power n minus 1 is the maximum value I can able to get. X means what? The number which you want to find out the complement. So the same, this logic I have written in the form of a formula. So this one I can call it as b minus 1's complement, and I can alternatively call it as what? 9's complement. 9's complement, right? What about the b's complement means? Simply we can able to write as b power n minus x, right? Why you are getting it as? See, earlier you have studied already. If I am going to have a number like 1 1 1 1 base 2 base 2, right? Meaning that it's a binary number. What is the complement of 1 1? Basically, you know, 1's complement you can able to write. You can able to write 2's complement. 1's complement means exchanging of ones with zeros, zeros with ones. So ones with 0, 1 with 0. This is what? 1's complement. How we are going to get the 2's complement? By simply adding plus to the 1's complement. Can you able to get the 2's complement? Yes, right? So 0 1. This is what? 2's complement. This logic you know or not? If you are going to exchange 1 with 0, 0 with 1, you will get the 1's complement. If you studied it earlier, right? If you are in studied earlier, I can derive it for once again. Try to observe what I said. You have to subtract it from the maximum possible value. What is the maximum possible value I can able to get if the base is 2 for a 2-digit number? Again 1 1 1 1. From 1 1 what I have to do? I have to subtract again 1 1 x. So are you going to get 0 0 or not? Yes, 0 0. Then it is called as 1's complement. For this, if you are going to add plus 1, I will get 2's complement. See, observe here for b power n minus 1 minus x, if I am going to add plus 1, are you going to subtract these two cancel? Then you are going to get b power n minus x or not? That is a complement. That is a b's complement for a radix b. Radix b. So try to solve this one. 45 base 10. See, if I am trying to say a number with base b, how many kind of complements will you going to get? 2. One is 9's complement is one possibility. Another one is 10's complement. 10's complement, right? Which one is the better one? That I will explain in the later part, right? So what is the 9's complement of 45? Simply you have to subtract it with the 99. 54. So just try to go with the procedure first. Next, what is the 10's complement of 45? 9's complement plus 1. So 55 base 10. Base 10. Okay. So try to solve this. For example, I am trying to have a number like 1 2 3 4 base 8. If I am saying that it's base 8, two kind of complements are possible. One is 7's complement and one is 8's complement, right? What is 7's complement value? You have to simply subtract with the maximum possible value. Maximum possible value is 8 power 4 minus 1. See, you are going to get confused here. 8 power 4 minus 1 is what? Decimal format. This is decimal format. Again, if you are going to convert into octal format, then you will get the value as 47. That is the maximum power value you are going to get. From that, you need to subtract 1, 2, 3, 4. So you are going to get 6, 5, 4, 3. This is 7th complement. For this, if you are going to add plus 1, you are going to get 6, 5, 4, 4. This is 8th complement. Okay. So try to do this. 121 base 3. What is the complement of 121 if it is base 3? So you are going to get again 2's complement as well as 3's complement. If it is 2's complement, you need to subtract from all 2's. So 101 base 3, 1 102. Is 2 is possible here? Yes. 102 base 3. 102 base 3. Okay. So this way you can able to get the complement of a particular number. Is it okay? Yes. See, now meaning that if I am going to have a number something like x, that number I can alternatively represent in the form of a some other form like y, so that I can able to use the same circuit for any kind of number. For example, let me take the same number again, 84 base 10, 84 base 10 and 6 base 10. 6 base 10. I would like to perform subtraction operation. What is the result? Right? It is direct answer because they are in our understandable format, that is base 10. As base 10, I can able to directly solve. So you are going to get the result as 78 base 10. 78 base 10. But if you observe guys here, so the same number I have to write in two ways. One is 84 minus 6. So while performing subtraction, you have to use some other kind of circuit, is it? Right? Instead of that, I can represent like this: 84 plus of minus 6. Plus of minus 6. This minus 6 also, I can write it, it's alternative. It's alternative. Its alternative means what? Some complement value. Some complement value. Right? So for minus 6 complement value, you have to find first. Right? So if I am going to find out the complement of minus 6, right? So actually 84 base 10 is as usual. For 6 base 10, 6 base 10, what is the complement of 6? So 99 minus 6, right? So okay, fine. So as per understandability, it is single line only. Single line minus 6 is 3. 6 is 3. But while trying to perform any kind of additional subtraction in any kind of computer systems, you have to make it equal number of digits, right? So then I can able to make here as 06, right? Then 99 minus 6 is 93. 93 base 10, meaning that what I did here, I have represented minus 6, which is in the system to positive number is equal to 93. Positive number equal, meaning that 93 is the complement of minus 6. Right? Now I can able to simply perform addition. Right? Now you can observe, right? The same data, I have used only the same circuit, that is of addition circuit. Now try to perform addition. 4 plus 3, 7. 8 plus 9, 70. 177. But what is the result we are expecting here? 78. 78, right? So here, what is the maximum space available for us to store the data? 2 bits are enough. 2 bits are sufficient. But extra carry is forwarded. This is what I can call it as overflow. Overflow, meaning that it is not sufficient to store the remaining data. That one I can call it as overflow. Right? The extra bit I can able to add it to the existing location space. 77 plus 1 is 78 base 10. Is these two are equivalent or not? But here computer what did? Is it done any kind of subtraction here? No. Just make it as addition only. But are we going to get the result or not? This is what the advantage of complementary of a system. Okay. So try to take out one more number, the same number 06 84. Both are of decimal number. I am trying to perform subtraction. What result do you need to get? Minus 78 base 10. This is the result you need to get. See, observe here. So for negative number you have to find out complement. 06 for 84 complement is 99 minus 84, 15, 15, and then you simply perform addition. Addition. So total is what, ma? 21, which is base 10. Is it equivalent? No, it is not equivalent. Then what you have to do? Can you find out any relation between these two? Complement of 21 is 78 or not? Yes. So what you can do now, simply you can perform again complement of the result. Complement of the result. Complement means from which number you need to subtract? 99. 99 minus 21 is 78 base 10. What about negative? How can we tell it is negative number or not? See, observe here. This is normal 6. Normal 6 means normal base x. Is it okay? Normal x. And this 15 is what? Complement of one number called y. I mean, I am assuming that 6 is x and 84 is y. What is complement of y? Complement of y. 15, okay. What is the formula that we are trying to derive here? 10 to the power of 2 minus 1 minus y. Minus 1. Right? So, here you can observe one important point. If you are trying to do, if I am going to have a number x and I am trying to perform complement of x, what you need to get here? 0. I need to get here 0. Right? So x and minus x, when you perform addition, you need to have 0 only. So we can simply call it additive inverse. Right? If you take the value of x, what is x? X bar b power n minus 1 minus x, which is equivalent to 0. If you are going to remove this one, what you are going to get here? B power n minus 1 is equal to 0. Meaning that when this particular equation is going to be satisfied, when you make b power n minus 1 is equal to 0, b power n minus 1 is equal to 0, then only our statement is correct. Then only our statement is correct. Right? In addition, in another form, what is b power n minus 1? Which is equal to x power n minus 1, maximum number, right? So, for example, if it is 2 power n minus 1, where n is 4, what is the maximum number? 4 ones. 4 ones. What, according to this formula, what we are trying to say? This is 0. And if you observe the same 4-digit number, can we get any 4-digit number like 0000? Will you get the value 0 or not? Yes. Meaning that in this particular representation, this is what kind of representation? B minus 1's complement. In B minus 1's complement, we are going to have two patterns. Which will be directed to same number. Is it a valid thing? No, that is not valid. So meaning that this is invalid kind of design. I hope you understood, right? So actually, with one kind of procedure, you are going to get the value 0. The same thing you are going to get with again 4 ones, but that is not the correct one. So this is the drawback what we are facing in b minus 1's complement. B minus 1's complement. Here try to observe, according to this logic, b power n minus 1 equal to 0. We are trying to simply make this as 0. We simply make it as 0. Meaning that 6 plus 15 is 21, which I am trying to say that x plus b power n minus 1 minus y. I am going to make this as 0, which is 21 base 10 x minus y. Am I right? Yes or no? Now, for this one, I am trying to find out complement. What is the complement of 21? 78 base 10. If I am going to find out the complement of 21, what about the complement of x minus y? Opposite side, right? That is minus of x minus y, right? So if I remove the minus here and if I move towards right side, x minus y equal to minus 78 base 10. Minus 78 base 10. So this logic you have to follow. So once you perform complementation, then again you have to append minus. So you are going to get as a minus 78 base 10. Okay. See, observe. So let me take one more example. Can you tell anyone any example? Any number? 43, 76. Okay. Both are of base 10. I am trying to perform subtraction. What you have to do, ma? So for negative number, you have to find its complement so that you will get the positive number, right? So 76. Try to tell. 76 and 99 minus 43 is 56. So value is 12. 7 5 is at 7 5 12. 12 plus 1 13. You got the carry. You can simply add here so that you will get 33 base 10. So this is also equivalent to this one. So our trying to do solving the procedure is correct. Okay. The same thing try to do in another format. Reverse 43 minus 76. You need to hit minus 33 base 10. So 43 is as usual. Minus 76 complement is 23. If you are going to add 66, right? So do you got any kind of carry here? If there is no carry, you have to first find out its complement, that is 33, which is x minus y, which is minus of x minus y. Complement is minus of x minus y. So you are going to get x minus y as minus 33 base 10. Minus 33 base 10. Okay, now see guys, here I will derive one procedure here. Try to observe. When you are trying to perform subtraction, try to first find out the complement of a negative number. Find out the complement of a negative number. After finding the complement of a negative number, whatever the result you got, if the result is going to generate any kind of a carry, remove that carry and simply add it to the result so that you will get the result. You will get the actual result. Similarly, see, observe here. Here this is what value, ma? X. This is b power n minus 1 minus y. Minus y. Right? I am trying to make this as 0. So I am going to get x minus y. If this x minus y generates a carry, I will simply add it to the plus 1. If it is not going to generate a carry, I am going to simply find out its complement and I am going to simply append its minus 1. This is the procedure you have to follow while trying to perform subtraction or to any kind of number system data. So, see, first one, try to find. So I am trying to tell for b minus 1's complement procedure. First find out b minus 1's complement number, and then if you are going to get the result x minus y result generates a carry, then you need to add it to the result. You need to add back to the result. That itself as a final result. Right? What is another case? If x minus y doesn't generate a carry, meaning that if it is not going to generate an extra bit, you can simply, you need to find out first complement. You need to find out complement, then you need to add negative symbol, then this will be your final. These are the two steps that you have to follow. Okay, see, try to solve the another one. Any number you can give. 121 and 110, not base 10, both are of different base. Try to perform subtraction. See, I will try to tell this one also. See, what is the values after subtraction? Right, 121 base 3 in decimal format. You have to perform multiplication, right? 1 plus 6 plus 9. 16. Very good. 16 base 10 and 110. 3 plus 9, 12 base 10. If I am going to perform subtraction, you need to have 4 base 10. You need to have 4 base 10, right? So now try to do the same procedure what we did. First 121 as usual, and what about 110 in its complement form? You have to subtract with the maximum positive value. Maximum positive value is triple two. Triple two, if you are going to subtract 1, 1, 2. 110 in decimal format is 13. 3 plus 9, 12. 0, right? Okay. So here the maximum positive value you are going to get triple two. From triple two you are trying to subtract 110, you are going to get 112, and then you are going to perform addition. If you are going to addition, what is the value you are going to get here? 3. 3. But is it correct? No. In if a so in base 3 radix system, there is no number such that which are greater or equal to 3, right? Then what you have to do? Again you have to convert into base 3 format. 3 you have to convert into base 3 format. What is the value? 3 convert into base 3 value. I think 10. Okay. Is it okay na? 3 converting into 3 1s are 3 10. This is in base 3. Now try to observe 4 you got. 4 is available. 4 is not available. Then what you have to do? You have to convert into again base 3 format. Base 3 format, 4 3s are sorry 4. If you are going to do it with 3, you are going to get 1 1. Now you got 3. 3 is available once again? No. Then what you have to do? You have to again remove this and you have to modify it with the base 3 system, that is 1 0. See, 1 is carry, that I made it directly here, right? So now according to our algorithm, if you are going to have a carry, what you have to do? You have to simply add it to the plus 1, that is 0 1 1, which is in base 3 system, right? Now in decimal system our value is 4 base 10. Is these two are correct or not? Try to cross check. What you have to do? Base 3 system trying to convert to decimal system, simply multiply with powers of 3. Are you going to get the 4 base 10 or not? So whatever the algorithm that we are trying to learn here is perfectly correct. If it is in b minus 1's complement. Okay, so try to do this one. See, up to now we have seen b minus 1's complement. Now let's see b's complement procedure. 84 and 6. 84 minus 6. What you have to do, ma? 84, okay. 06. Earlier you have written in the form of 9's complement. Now we need to try to write in the form of 10's complement. For that, what you have to do? 9's complement plus 1. That is 93 plus 1. 94. 94. Now we can able to perform addition. Are you going to get 8 and 178? What is the result of actual data? If it is in base 10, 78, right? So we got the data other than the carry. We got the data other than the carry. So we can simply discard this. There is no need of this one. Okay. Similarly, try to take out 06 minus 84. You are going to get minus 78 base 10. 06 is as usual. 84 complement is 84 b's complement means 10's complement. So 9's complement is 15, 10's complement is 15. So you are going to get 21, right? Which is not our expected result. So again you have to take its what? Complement. So 10's complement is 16. 9's complement is 15, 10's complement is 16. 16 plus 6 is 22. 22. 22 is exactly complement of 78, right? So what you have to do here? You have to perform complement. Complement, if you are going to do, you are going to get 78 base 10. But if you observe here, this is x, this is b power n minus 1 minus y. So this is what? 16, sorry, b's complement. So b power n minus y. So we are making it as b power n as 0. Why we will make it as b power n as 0? To make x plus x complement as 0. To make x plus, see, if I am going to have x plus x complement as 0, x is as usual value, b power n, x complement is what? B's complement, b power n minus y, right? If I want to, if I want to make, if I want to make it as 0, b power n should be 0. That's why b power n at 0, that you are going to get as x minus 5. X minus 5. If I am going to try to perform complement here, this should be minus of x minus 5. So x minus y is what? Minus 78 base. Minus 78 base. So try to take with another example. Uh, this one. 76 and 43. What is the value? 76. This is 54. Sorry, 56. 56 is 9th complement. 57 is 10th complement. So 13, 133, 1 discarded. So are you going to get the result or not? Yes, 1 discarded. Similarly, 43 minus 76. So 43, 23 plus 1, 24. You are going to get 67. You need to find out its complement. That is 33. Further, you need to append minus. Right? So means here what you have to do, ma? If it is in B's complement, if it is in B's complement, when you are trying to perform work with B's complement, try to find out first B's complement for the negative number. After that, whatever the number that you are trying to subtract, the result will be, if it is going to generate a carry, just discard the carry. That is second step. If there is no carry, if there is no carry, you have to find its complement. You have to find its complement, and then you have to add sign. This is the final result. Final, right? So this is the way you can able to perform subtraction of a number in uh, any kind of system, operating systems. Okay. So finally, I can conclude that like any kind of negative numbers are stored in the form of complements. You can be able to store in the b minus 1's complement or in the b's complement. If it is going to store in the b minus 1's complement, what is the problem? Observe here. Observe here. According to our assumption, the same two patterns, 4 ones will be equal to 0 and 4 zeros also will be equal to 0. Whereas coming to in b's complement is that it is possible b power n is equivalent to 0. What is b power n? See, b power n minus 1 is the maximum possible number. After that, next number you are going to get is the next number as b power n. So, first initial number is 4 ones. Next, whatever number next number you are going to get, that is 1 000. Our system is capable of storing only 4 digits. Then what is this value? 0. 0 is equal to 0 only. So, all 4 zeros equivalent to 0. This 0 is also equivalent to 0. There is no problem in that. So this is correct. So that's why most of the systems are all following B's complement only, and this is the most useful one. Okay. So if you observe here, if I am going to take the number system, one is unsigned number system, another one is signed number system, right? So basically, if you are going to have 3 bits, if you are going to have 3 bits like 2 power 0, 2 power 1 and 2 square, you are going to get these combinations, right? Is it okay? Right? So we are going to get 8 combinations starting from 0 to 7, right? So in unsigned number system, unsigned means there is no signed representation. If there is no signed representation, how many values you can able to store? 7 with help of 000, 1, 2, 3, 4, 5, 6, 7. Is it okay? So 7 I can able to represent as 111. Whereas coming to signed number representation, again it is classified into 3 types, right? According to our explanation. So if you observe, one is signed magnitude representation. Signed magnitude representation. So in signed magnitude representation, if I am going to have 3 bits, one bit should be reserved for what? Sign. One bit should be reserved for sign bit, right? So if I am going to have 3 bits, one bit should be reserved for sign bit, right? So then, with the help of other 2 combinations, how many values you can able to generate? Maximum 3. I mean 4 values you can generate from 0 to 3. So 0 0, 0 1, 1 0, 1 1. Right here, in place of this one, I can able to place either 0 or I can able to place 1. Right, if I am going to place 1, again 0 0, 0 1, 1 0, 1 1. Right, then what is this value? This value is 0, 1, 2, 3, minus 0, right? So minus 1. So I hope you understood, right? This value is 1, this represents minus. This value is 2, this represents minus. Value is 3, represents minus. Observe now, right? So in signed magnitude representation, we are going to have two kind of patterns, 000, 100, equate to same 0. Is there anything like positive 0 and negative 0? No, there is no such thing. That is one drawback. And also the thing is, if you are going to work with any kind of signed magnitude representation, you need separate kind of hardware. Hardware means separate kind of circuit, right? You need to identify what is the MSB bit, what is the LSB bit, all those things you have to identify, you have to make it some kind of other kind of working procedure, right? So that is the reason they moved to work with the complementary system. Among those, one kind of complementary is ones complement and another is two's complement, which we studied just now, right? So what is ones complement? Just make it converse of actual value. If it is triple zero, its converse is triple one. Converse is triple one, right? So for triple one, what is the value you are going to get? In one's complement, if I am going to give the value as triple one, means it is zero. Try to observe. Triple zero, its complement is 1 1, which is equivalent to again 0. Is it okay? Right? If I am going to say that 0 0 1, 0 0 1, its complement is what? Double 1 0, that is 1. That is 1. So this is what, ma? Normal 1 or complement 1? Complement 1, meaning that it should be minus 1, it should be again minus 0 only. Right? There is no meaning for minus 0. That's why I didn't write. Like for your understanding, I am going to make it as minus 0. Right? So 110 represents what? Minus 1. Is it okay? Right? So I have taken the same normal number. I am going to make it complement. Complement means opposite to the value. Opposite to the value, right? So similarly, 0 1 0, 1 0 1. This is 2, which means 101 as minus 2. 101 in one's complement will act as minus 2. 101 will act as minus 2. Right? Next, 100, 011 will act as minus 3. See, 100 value is what? 100 is actually 4. 100 is actually 4, right? But it will act as minus 3. Why? Its complement is minus 3 itself. That's it. Its complement is minus 3. Similarly, if you are going to represent like 000, its complement is 0 only. And 001, its complement is 1. And its complement is 2. Is it sufficient? One minute. See, try to, don't get confused. I just divided into two parts only. One is positive part, another one is negative part. So I hope you got up to here. 100 will act as minus 3. And the remaining part as it is above should be worked as it is. Like it should be 0, 1, 2, 3. 0, 1, 2, 3. Similarly, in 2's complement also, it will work as it is. 0, 1, 2, 0, 1, 2, 3. And what about the 2's complement representation of this 100? 100, 100, like if you take any number 100, which is actually what value? 4. 4, right? What is 2's complement? 011. For this, if you are going to add plus 1, you are going to get 10, 10, 100, 100, right? What is the meaning of this one? Minus 4, right? You have given the 4 as input. I am going to take its complement. Take its complement. So complement of a number is negative number, minus 4. Similarly, take out 101, 010. For this plus 1, 011. 101 is what value? 5. 5. What about its complement? 011. Is there a relation? Are you going to find out? No. No, that is not the thing. Right? Here, you have to find out. See, this is for your understandable I have taken. Don't always take these values, right? So next see, if I am going to represent any data with 3 bits, with 3 bits, how many values are you going to get? I have a question for you. If I am going to have a number, I am going to have a number 12 in base 10, how many minimum bits are required in order to represent the number 12? These 3 bits are sufficient? Yes, sir. No. 4 bits are required in order to represent the number 12. Number 12. Similarly, if I am going to have a 2's complement number, in order to represent the number 5, is it possible to represent the number 5 in 3-bit system? Is it possible? It is not possible. So what you have to do now, see, try to observe. Here 0, 1, 2, 3 are possible values. Positive values. What about the negative values? If you take the number 3, number 3 value is what? 0, 1, 1. 0, 1, 1. For this 1's complement is 100. For this 2's complement is 101. If I am going to have 101, which means what? Minus 3. I have taken the number 3. I just written the binary system. I find out the 2's complement. I got the 101, which is minus 3. Meaning that wherever 101 is there, in that particular location, I am going to write it as minus 3. Minus 3. Similarly, if I are going to find out, it should be minus 2. It should be minus 2. Observe, if you want, try to take out the value of 1. Value of 1 is 001. Try to take out its complement 110. Add plus 1, so 2's complement we are going to get. That should be 111. Wherever 111 is there, that is complement of 1 in 2's system. Okay, now fine. This way you can able to do. See here the point is, so these are the points which are important for the gate. So here, if you would like to represent any kind of a number, any kind of a positive number, that is unsigned number representation. If I am going to have 3-bit system, what is the maximum values I can able to get? Can I generalize the formula, which you already know? 2 power n minus 1. Is it okay? Right? What is n here? 3. 2 cube is 8 minus 1 is 7. So total maximum number is 7 or not? Maximum number is 7. So what is the range of values that you can able to generate if you are going to have a 3-bit system in unsigned representation? 0 to 7. That is 0 to 2 power n minus 1. What about signed magnitude representation? See, observe here, the values are from, if you observe here, one is 0 to plus 3. Another one is minus 0 to minus 3. See, according to logic, there is no minus 0. But the way we got here, I have just written it. Right? Is there any use of representing 0 and 0 in both ways? No, we can able to have only one way. So, what is the range? How can we generalize this one? See, if you observe this thing, the entire number of numbers generated. What is the number of numbers generated? So if I am going to have 3-bit system, total numbers are generated are 2 power n. 2 power n, that is 8. Right? So that is divided into two parts. First half of the part is for positive and second part is for the negative numbers. Right? So how we are going to divide an n-bit system? 2 power n by 2. 2 power n by 2. So each part will contain 2 power n minus 1. 2 power n minus 1. If it is this sign magnitude representation, what is this representation? Positive values are ranged from 0 to 2 power n minus 1 minus 1. What about the negative values range? 0 to minus 2 power n minus 1 minus 1. Is it okay? If you want, you can just substitute the number 3. 2 square minus 1 minus 4. Sorry, this should be minus. Right? 2 square minus 1 is minus 3. Okay. Similarly, what about this representation in ones complement? What about in ones complement? Are you going to get the same or not? Because the range of numbers are from 0 to 3, 0 to minus 3. So the range is from again. So simply I can write like minus of 2 power n minus 1 minus 1 to plus of 2 power n minus 1 minus 1. Is it okay? What about the 2's complement? See, this is the advantage. So in ones complement or in sign magnitude representation, we can able to define only 7 unique elements. Whereas coming to 2's complement, are you going to get 8 unique elements? Because the minus 4 is there. So what is the range I can able to define? Minus of 2 power n minus 1 to plus of 2 power n minus 1 minus. Okay na? I think this generalization is okay for you, right? So now, so with respect to this concept, so if I am going to have, if I am going to have a number like minus 3, minus 3 in decimal number, minus 3 in decimal number, which is in 2's complement representation, which requires to represent in 2's complement, how many number of minimum bits are required? See, question is, I want to represent minus 3, which is in decimal number system, want to represent in 2's complement representation. How many bits are required? Observe, minus 3. If you want to represent 2's complement, what is the value? 101. How many bits are required minimum? 3. That is the answer. So the answer is 3 bits are minimum required in order to represent the minus 3. So the same thing, if I am having a 15 with base 10, I want to represent the same number in 2's complement. How many number of minimum bits are required now? 5. How? Is it okay? Is 5 bits are enough? Right? So if you want, you can just, so 15 means I can write as like this, 4 ones, right? For this, try to find out the complement, 4 zeros. For this, you can able to add plus 1, then you are going to get triple zero one, triple zero one, right? So this is 2's complement of 15, 2's complement of 15, right? 4 bits are required, 4 bits are required. So try to solve this. I mean, try to solve means you have to make it generalize also. How can you do that? So is 15 is 4 ones only, right? Hmm. What is the ones complement of 4 ones? 4 zeros. Then I am going to add plus 1. Then it is 2's complement. So triple zero one, triple zero one. See, this represents what? 1 or minus 15 or minus 15. See, this is 15. 15. 15 in 2's complement is equivalent. If I am going to find out, this will be equivalent to minus 15. But the question is, in order to represent the number 15 in 2's complement, how many bits are required? See, I mean, if I am going to have 4 bit space, 4 bit space, I can able to represent minus 15. I can able to represent minus 15. If it is going to support minus 15, can it support plus 15? if it supports plus 15, if it supports minus 4, can it supports plus 4? According to this particular like generalogy, it is not supported, because in order to represent more than negative number positive side, you have to require one more bit. So 4 bits are not sufficient. So you can go with the 5 bits. Go with 5 bits, right? So basically in the examination, this will be not like a simple numbers. So it will have a maximum numbers. So what you can do now? So in 2's complement, what is the maximum number you can able to generate? Generally, what is the range of numbers you can able to generate? Minus 2 power n minus 1 2 plus 2 power n minus 1 minus 1. Meaning that if I are going to take a scale of like this, my 0 will be like this: 2 power n minus 1 minus 1 minus 2 power n minus 1. What value they asked? They asked 15 here, which is somewhere, right? So in order to represent this 15, I have to find out the n value. So this n value should be compulsory greater than or equal to 15. See, observe. So what is the maximum number I can able to generate? 2 power n minus 1 minus 1, which should be greater than or equal to the decimal number 15. Now try to solve. 2 power n minus 1 greater than or equal to 16. So which is equivalent to 2 power 4, n minus 1 greater than or equal to 4, n greater than or equal to 5. N greater than or equal to 5, right? So earlier I had said like a kind of a general overview example. Now with the help of some kind of logic, I made it as conclusion. So here compulsory n value should be greater than or equal to 5 only. Without the greater than or equal to 5 bits, it is not possible to represent the 50. Right? Similarly, what about minus 15? What about minus 15? Is 4 bits are sufficient? Yes, try to check that. Try to check it. Right? So minus 15 is available here. So minus 15 is greater than or equal to minus of 2 power n minus 1. Right? So 2 power n minus 1 should be greater than or equal to 15. Is it okay? Right? Now try to check. 2 power 4. 2 power 4 is 16, right? 2 power 4 is 16, right? So don't go with approximate values. Try to find out the exact values, so that you will get clear idea. So how we are going to solve this one? If you take n value 4, if you take n value 4, is this equation is going to be satisfied? No. Take out the n value 5. Take out the n value 5. So if you take out the n value 5, that means 2 power 5 minus 1, that is 2 power 4, which is greater than or equal to 15. Which is greater than or equal to 15. So in order to represent the minus 15, in 2's complement reference system, I require compulsory 5 bits. I require compulsory 5 bits. But according to this logic of representing a 15, see, this is completely different and this is different. This is minus 15 and this is plus 15. See, you should not compare these values. Okay, so this is correct. So number of bits are required to represent the minus 15 is 5. Okay. So similarly, like for example, here try to think, if I am going to take these values, I hope it is visible. So if you would like to get the value minus 3, if you would like to get the value minus 3, how can you get this value? Can I have any generalization? Right? I will take the new slide only. If you take here, if it is unsigned number representation, if you want to have the number 7, it should be 2 power 0, 2 power 1, 2 square, 1 into 2 square plus 1 into 2 power 1 plus 1 into 2 power 0, which is 7. Right? So this is one kind of unsigned representation formula. What about the signed representation, signed magnitude representation? You have to perform addition of all the numbers 2 power 0, 2 power 1 and so on and so on. So you may get positive sign or you may get negative sign. For the last bit, so last bit represents what? Sign magnitude, right? So last bit represents sign magnitude. So that should be multiplied with powers of minus 1. Minus 1 power MSB bit. Right, observe. If I am going to have a number like 110, number 110, what is the signed magnitude of this actual decimal number? This is what? So you have to multiply addition on all these things. So up to here it is 2. 2 into minus 1 power, what is MSB? 1. Minus 1 power 1 is minus 1. Minus 1 into 2 is minus 2. Which is equivalent to 110 or not? Minus 2 is 110. 110. So like this, if you are going to find out any kind of rule for one's complement, you cannot able to get anything. You cannot able to get any kind of thing. Okay. So if you want, you can able to try to find, but there is no generalization you are going to get. Whereas coming to 2's complement, it will be like 2 power 0, 2 power 1, 2 square and so on and so on. The most significant bit is minus 2 power n. Minus 2 power n. Then you are going to get that. For example, try to take out this value only. Triple one. Triple one. What is the meaning of this one? 1 into 2 power 0 plus 1 into 2 power 1 plus 1 into minus 2 power n means what? 2 square minus 2 square. Normal n value only. Right? So then what is going to happen? Minus 4 plus 3. Minus 4 plus 3, which is equal to minus 1. Is triple one equal to minus 1 or not? Is triple one equal to minus 1 or not? So check out anything. Take out 100. Take out 100. 100 means 0 into 2 power 0, 0 into 2 power 1 plus 1 into 2 power, sorry, minus 2 power 2. So you are going to get minus 4. Minus 4. Right, guys, try to observe. I am trying to modify a small thing. 1100. What is the value? Minus 4 only. Why? If you are going to solve again, you are going to get minus 4 only. Why? It is consecutively multiples of 2 only. This is what? Minus 8 plus 4 plus 0 plus 0. You are going to get plus 0. So meaning that, so for example, triple one I am going to write it as, what is the value this value? What is the value of this in 2's complement? Minus 1. Why? Even you are trying to add all these things, the last bit is sum of all the remaining. Right? So I hope you understood. Is it okay? Yes. So sometimes the gate question will be related to this one. Okay. So if you observe here the logic, I am able to represent unsigned numbers in some format like powers of 2 powers, and signed magnitude representation I am going to represent some kind of formula, and 2's complement I am going to represent some kind of formula. If I are going to represent in some kind of formula, those I can call it as weighted codes. Weighted codes. What are the meaning of weighted codes? Each and every location have a particular value, and if I am going to perform some kind of expression, I am going to yield the same result. Each and every location having some weight. Right? Here if you observe, it is powers of 2. 2 power 0 with index position, 2 power 1, 2 power with index position, 2, and so on. Here you are going to have powers of 2, and the last position having minus power some MSB bit. Similarly, if you are going to have here all having powers of 2 and the last bit having minus 2 power index position. So everything having some weight. So that's why we call it as weighted codes, and we can call it as, we can alternatively call it as weighted codes. Right? And what about the ones complement? Will comes under unweighted codes. Unweighted codes, meaning that if you are going to represent some weights, you are not able to generalize the data. You are not going to generalize any expression for it. Then I can call it as unweighted codes. Okay, now. For example, guys, so I am going to have, so try to write the question. I am going to have, a 5-digit number. I am going to have a 5-digit number, 5-digit number, or I can call it as a 5-bit number in 2's complement. 5-digit number in 2's complement. What is that maximum value? I mean, what is the maximum number that can be generated with help of 5 digits in 2's complement? What we can do, ma? 2 power minus 1. This is maximum positive number I can able to generate, right? So what they are saying it is a 5-bit number. 5-bit number. Place in place of n with a value 5. So place 5, 2 power 4 minus 1. This is 15. So meaning that with the help of a 5 bits in 2's complement, I can able to represent maximum of 15 decimal number. Right? For example, I am going to have minus 16 base 10. Minus 16 base 10 in 2's complement representation. In 2's complement representation, can we able to represent with 4 bits? Minus 16. Is it possible to fit minus 16 base 10 in 2's complement representation of 4-bit representation? Right? So the simple thing is it is not possible. So it is not possible. So basically, if you observe the formula, minus 2 power n minus 1 to plus 2 power n minus 1 minus 1, right? If you are going to substitute the value of 4, you are going to get minus 2 cube 2 plus 2 cube minus 1, meaning that minus 8 to plus 7 I can able to place, but they have given as minus 16, so it couldn't possible to fit this value. Okay, fine. So with the help of this concept, I can able to extend, like if I am going to have a number, like for example, uh, if it is something like 0 double 1 0, 0 double 1 0, right? So assuming that This is normal positive number. Assuming that normal positive number plus 6. Plus 6. Can I extend it to something like 8-bit system? See, my point here is it is 4-bit system. 4-bit system. So I can able to write 0110 for positive 6. Can I extend the same with 8-bit system? Yes or no? I can extend. What you can do simply, you can able to simply add remaining 4 zeros. There is no problem. What about if it is minus 6? See, 1, 1, 1, 0. If it is, so it is minus 6, right? It is minus 6. What about in 8-bit system? What we can do? So sign bit should be separated with the remaining data 1, 1, 0, and you have to fill up with the 5 places, I think. 5 places. This sign bit should be taken with the last one, and all the remaining places should be occupied with 0. So this what I can call it as sign bit extension. Sign bit extension. So how we are going to extend the uh, places of the storing data, right? If it is 4-bit, okay. If it is 16-bit, you have to extend it. How we are going to extend? Okay. The same number, for example, if it is in ones complement, if it is ones complement, right? So plus 6 is actually what? 0, 110, right? If it is in ones complement, what is its value? 1001. 1001, right? So which is in which kind of platform? 4-bit system. What about I would if I would like to extend it in the 8-bit system? What about the same plus 6 in 8-bit system? What we can do here? Simple thing, you can just simply write 8-bit system for the actual data of plus 6. 8-bit system, if you are going to write 4 zeros, 0110. For this, if try to write the complement, what will happen? 111 1001. So this is 8-bit. Nothing. There is no problem. What about if it is in 2's complement? I think this is 1's complement. What about if it is 2's complement? Right? So basically, you are going to have plus 6, which is from 0110, and 1001 is 1's complement, and if I am going to add plus 1, you are going to get 2's complement. 1010. 1010 is 2's complement. Is 2's complement. If the same thing of 2's complement number in any kind of sign bit extensions like 8-bit space, then what is going to happen? Can you write the same procedure as like as earlier one? See, if you write earlier, there is a mistake. That should not happen. After the result, how many number of bits required? That many number of bits you can able to add, and you can able to simply place all ones. Why all ones? What is the formula for 2's complement number? Minus 2 power n, minus 2 power n, 2 power n minus 1, 2 power n minus 2, and so on, right? Even you are going to write any number of ones. Is there any change in this value? There is no change in this value. It is always going to be minus 6 only. If you want, you can able to calculate, right? So try to perform. This is what? Minus 2 power minus 2 cube plus 2 square plus 2 power 1. Minus 2 cube is what? Minus 8 plus 2, which is equivalent to minus 6. If you want, you can able to include all these numbers. Again, you are going to get only minus 6 only. So when you are trying to perform in 2's complement number, just simply extend the remaining number of bits with the 1.